Tonight, we're going to explore one of the most violent events in the universe, a supernova, the explosion of a massive star. An event so energetic that for a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. An event that releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. And here's what most people don't realize. Without supernovae, you wouldn't exist. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged inside massive stars and scattered across space when those stars exploded. By the end of tonight, you'll understand exactly how that process works and why the death of a star is one of the most important events in the universe. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When most people hear about a supernova, they imagine a star blowing up like a bomb. Quick, sudden, violent. And that's not entirely wrong. But the reality is far stranger and more complex than a simple explosion. A supernova isn't just a star blowing apart. It's the catastrophic conclusion to a battle that's been raging for millions of years. A battle between two fundamental forces. Gravity pulling inward, trying to crush the star into nothing, and pressure pushing outward, generated by nuclear fusion in the star's core. For most of a massive star's life, these forces balance perfectly. The star sits in what astronomers call hydrostatic equilibrium, stable, peaceful, generating energy through fusion, radiating light and heat into space. But this balance can't last forever. Eventually, the fuel runs out. And when it does, gravity wins. Catastrophically. Let's start with what kind of star becomes a supernova. Not all stars can do this. Our sun won't become a supernova. Neither will most stars in the galaxy. You need a massive star. Specifically, you need a star with at least 8 times the mass of our sun. Anything smaller dies more quietly, becoming a white dwarf after shedding its outer layers as a planetary nebula. But massive stars, stars between 8 and about 150 solar masses, these giants are destined for violent ends. The most massive stars are rare. Only about 0.13% of stars are massive enough to go supernova. Most stars are small red dwarfs, dim and long-lived, burning their fuel slowly for trillions of years. Massive stars live fast and die young. A star 10 times the mass of the sun might live only 20 million years. A star 25 times the sun's mass might last only a few million years. A star 50 times solar mass might survive less than 4 million years. Compare that to our sun, which will live for about 10 billion years total. It's already been around for 4.6 billion years and has another 5 billion to go. Massive stars burn through their fuel at an incredible rate because they need to generate enormous pressure to support their own weight. More mass means stronger gravity trying to collapse the star. Stronger gravity requires higher core temperatures to generate enough pressure to resist collapse. Higher temperatures mean faster fusion rates. Faster fusion means the fuel gets consumed quickly. Here's how a massive star lives its life. It starts like any star does. A cloud of gas, mostly hydrogen, collapses under its own gravity. As the cloud collapses, it heats up. The center gets hotter and denser. Eventually, the core reaches about 10 million degrees. At this temperature, Hydrogen nuclei, moving at high speeds, collide with enough force to overcome their electrical repulsion and fuse together. 4 hydrogen nuclei combine through a series of steps to form one helium nucleus. This process releases energy. A lot of energy. That energy creates pressure that pushes outward, stopping the collapse. The star reaches hydrostatic equilibrium and settles into the main sequence phase of its life. For a massive star, this hydrogen burning phase might last a few million years. The star fuses hydrogen in its core, converting about 600 million tons of hydrogen into helium every second if it's similar to our Sun. More massive stars burn even faster. But eventually, the hydrogen in the core runs out. Not all the hydrogen in the star, just the core. The outer layers still contain plenty of hydrogen, but the core is now almost entirely helium. With no hydrogen left to fuse, fusion stops in the core. Without fusion generating pressure, the core contracts. It collapses inward under its own weight. This collapse releases gravitational energy, heating the core. Around the contracting helium core, there's now a shell of hydrogen. This shell gets compressed by the weight of the layers above it, compressed and heated by the hot core below it. The temperature and pressure in this shell become high enough for hydrogen fusion to begin there. So now the star is burning hydrogen in a shell around the core, while the core itself contracts and heats. The energy from this shell burning causes the outer layers of the star to expand enormously. The star swells up, becoming a red supergiant. Its surface cools as it expands, which is why it looks red. But the core keeps contracting, getting hotter and denser. Eventually, the core temperature reaches about 100 million degrees, hot enough for helium fusion to begin. 3 helium nuclei fuse to form carbon. This is called the triple alpha process. 2 carbon nuclei can fuse to make neon or magnesium. Helium can fuse with carbon to make oxygen. The core now burns helium, creating carbon and oxygen. This generates pressure again, stopping the core's contraction. The star has reached a new equilibrium. But helium burns much faster than hydrogen. A massive star might burn hydrogen for several million years, but burn helium for only a few 100,000 years. Once the core helium is exhausted, the same process repeats. The core contracts and heats up again. A shell of helium begins burning around the now carbon-oxygen core. The star's structure is becoming like an onion, layers upon layers of different elements, each burning in shells around the inert core. When the core reaches about 600 million degrees, carbon fusion begins. Carbon fuses into neon, magnesium, sodium. This phase lasts maybe 1,000 years. Then, carbon runs out in the core. The core contracts and heats up. At about 1 billion degrees, neon fusion begins. Neon burning lasts about 1 year. Then, oxygen fusion at about 1.5 billion degrees. Oxygen burning lasts about 6 months. You can see the pattern. Each stage happens faster than the last. The star is running out of road. Finally, the core reaches temperatures around 3 billion degrees. Silicon fusion begins. Silicon and other elements fuse into iron and nickel. This phase lasts about 1 day. 1 day. That's all the time a massive star gets at this final stage. And then it's over. Here's the critical point. Every fusion reaction up to this point has been energetically favorable. Fusing hydrogen into helium releases energy. Helium into carbon releases energy. Carbon, neon, oxygen, silicon, all the way up the periodic table. Each fusion releases energy. The star can support itself by burning these fuels. Iron is different. Iron is the most stable nucleus. It has the highest binding energy per nucleon of any element. Fusing iron into heavier elements doesn't release energy. It requires energy. You have to put energy in to fuse iron into anything heavier. So when the core is full of iron, fusion stops. There's no fuel left that can generate energy through fusion. The core is supported only by electron degeneracy pressure. This is a quantum mechanical effect. Electrons are fermions, particles that obey the Pauli exclusion principle. No two electrons can occupy the same quantum state. When you compress matter to extreme densities, you eventually run out of available low-energy quantum states. Electrons are forced into higher and higher energy states. This creates a pressure that resists further compression. For a while, this degeneracy pressure holds the core up. But there's a limit. The core keeps accumulating iron from the silicon-burning shell above it. The core mass increases, and there's a maximum mass that electron degeneracy pressure can support. This limit is called the Chandrasekhar limit, named after Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The Chandrasekhar limit is about 1.4 times the mass of the Sun. When the iron core exceeds this mass, electron degeneracy pressure can't hold it up anymore, and the core collapses. This is where the supernova really begins. The collapse happens fast, incredibly fast. The core, which might be about the size of Earth, collapses in less than 1 second. In a fraction of a second, the core shrinks from thousands of kilometers across to about 20 kilometers across. That's roughly the size of a city. The density becomes unimaginable. Matter is compressed to nuclear densities, about 100 trillion kilograms per cubic meter. A teaspoon of this material would weigh about 100 million tons. As the core collapses, several things happen simultaneously. First, the electrons and protons in the core are squeezed together so hard that they merge. Electron plus proton equals neutron plus neutrino. This is called neutronization or electron capture. It removes the electrons that were providing degeneracy pressure. That speeds up the collapse. Second, the iron nuclei themselves start breaking apart. At these extreme temperatures and densities, the iron nuclei disintegrate into individual protons and neutrons. This process is called photodisintegration. It absorbs enormous amounts of energy. All the energy that was released when that iron was originally formed now gets absorbed, breaking it back down. This removes energy from the core, cooling it, reducing pressure. That also speeds up the collapse. Third, enormous numbers of neutrinos are produced. Neutrinos are nearly massless particles that barely interact with matter. Most neutrinos pass through Earth without hitting anything. They're produced in vast quantities during the core collapse. About 10 to the 58th power, neutrinos are produced in a core collapse supernova. That's a 1, followed by 58 zeros. More neutrinos than there are atoms in several Earth masses. These neutrinos carry away about 99% of the energy released in the collapse. The actual explosion, the light and blast wave that we see, is only about 1% of the total energy. Most of the energy escapes as neutrinos. The collapse continues until the core reaches nuclear density. At this point, something remarkable happens. the strong nuclear force kicks in. Protons and neutrons attract each other through the strong force, but only at very short ranges. When neutrons are packed together at nuclear densities, they touch each other. The strong force becomes repulsive at these tiny distances. Suddenly, the core material becomes incompressible. It can't be crushed any further. The infalling material hits this incompressible core and bounces. This creates a shock wave, a wall of pressure and energy moving outward through the star. This shock wave should, in theory, blow the star apart. But there's a problem. As the shock wave moves outward, it has to push through the infalling outer layers of the core. Those layers are incredibly dense. The shock wave loses energy. It also loses energy to photodisintegration, breaking apart the heavy nuclei it encounters. Within milliseconds, the shock wave stalls. It gets stuck a few hundred kilometers from the center. The infalling matter is too dense. The shock can't push through it. For decades, this was one of the biggest mysteries in supernova physics. How does the explosion actually happen? The bounce creates a shock wave, but the shock stalls. What revives it? What gives it the energy to push through and blow up the star? The answer involves neutrinos. Remember those 10 to the 58th power neutrinos produced during the collapse? Most of them escape without interacting with anything. They just fly out through the star at the speed of light. But at the extreme densities in the core, even neutrinos can't escape immediately. The outer core is so dense that neutrinos actually get trapped for a moment. They scatter off neutrons and protons. They get absorbed and re-emitted. They deposit energy as they work their way out. This region where neutrinos are trapped is called the neutrinosphere. It's like a photosphere, the visible surface of a star, but for neutrinos. As the neutrinos diffuse outward from the neutrinosphere, they pass through the region behind the stalled shock wave. A tiny fraction of these neutrinos interact with the matter there. They deposit energy. They heat the material. This heating revives the shock wave. It's like giving the shock a second wind. With this extra energy from neutrino heating, the shock starts moving outward again. It pushes through the infalling layers. It accelerates. It tears through the silicon-burning shell, the oxygen shell, the neon shell, all the layers of the star. Within a few hours, the shock wave reaches the surface of the star. When it does, the star explodes. The outer layers are blown into space at speeds of 10,000 to 30,000 kilometers per second. That's 3 to 10% the speed of light. The explosion releases about 10 to the 46th power joules of energy. That's equivalent to about 100 times the energy our sun will radiate in its entire 10 billion year lifetime. Released in seconds. For a few weeks, the supernova can outshine its entire host galaxy. One star outputting more light than hundreds of billions of normal stars combined. This light comes from multiple sources. Initially, it comes from the shock wave, heating the outer layers to millions of degrees. Hot gas radiates intensely. Later, the light comes from radioactive decay. The explosion creates enormous amounts of radioactive isotopes. Nickel-56 is produced in the explosion. It decays to cobalt-56 with a half-life of about 6 days. Cobalt-56 decays to stable iron-56 with a half-life of about 77 days. These decay processes release energy that keeps the supernova bright for weeks or months. The famous supernova SN 1987A, which exploded in the Large Magellanic Cloud in 1987, was powered by the decay of about 0.07 solar masses of nickel-56. That's about 23,000 Earth masses of radioactive nickel. From Earth, we see a new star appear in the sky. It brightens over a few days, reaches peak brightness, then slowly fades over weeks or months. To ancient astronomers who believed the heavens were eternal and unchanging, these guest stars were deeply unsettling. Chinese astronomers recorded supernovae as far back as 185 CE. The most famous historical supernova is probably SN 1054, observed by Chinese and Arab astronomers in the year 1054. It was visible in daylight for 23 days and remained visible to the naked eye at night for about 2 years. The remnant of this explosion is now the Crab Nebula, one of the most studied objects in astronomy. Another famous supernova was observed in 1572 by the Danish astronomer Tycho Brahe. Tycho's supernova was brighter than Venus and visible in daylight. It challenged the Aristotelian view that the heavens were perfect and unchanging. If stars could appear and disappear, the heavens weren't eternal. They were subject to change, just like Earth. This was philosophically revolutionary. In 1604, Johannes Kepler observed another supernova in our galaxy. Kepler's supernova was also visible in daylight. These two supernovae, Tycho's and Kepler's, helped change how people thought about the cosmos. Since 1604, no supernova has been observed in the Milky Way. We're overdue. Statistical studies suggest that supernovae occur in our galaxy at a rate of about 1 or 2 per century. We haven't seen one in over 400 years. But that doesn't mean they haven't happened. Our view of the galaxy is obscured by dust. Supernovae on the far side of the galaxy, or in the galactic plane where dust is thickest, might be completely hidden from view. Astronomers are watching. Amateur astronomers regularly scan the sky, looking for novae and supernovae in nearby galaxies. Automated surveys monitor millions of stars. When the next Milky Way supernova occurs, we'll know within hours. Supernovae come in different types. The kind I've been describing, core collapse of a massive star, is called a Type II supernova. More specifically, that classification is based on the spectrum of the supernova. Type II supernovae show hydrogen lines in their spectra. That makes sense because the outer layers of the star, the ones being blown off, are mostly hydrogen. But there are also Type I supernovae, which don't show hydrogen lines. Type 1b and Type 1c supernovae are thought to be core collapse events in massive stars that lost their hydrogen envelopes before exploding. Stellar winds can strip away the outer hydrogen layers of a very massive star. Or, if the star is in a binary system, its companion might gravitationally strip away the hydrogen. When the core collapses, there's no hydrogen left in the outer layers. So the spectrum shows no hydrogen lines. But there's another kind of Type I supernova that's completely different. Type 1a. Type 1, a supernovae don't come from core collapse. They come from white dwarfs. A white dwarf is the remnant of a low or medium mass star. When our sun runs out of fuel, it will shed its outer layers as a planetary nebula and leave behind a white dwarf core. White dwarfs are supported by electron degeneracy pressure. They're not burning fuel. They're just slowly cooling off, radiating away their heat over billions of years. Normally, a white dwarf just sits there, stable, cooling forever. But if a white dwarf is in a binary system with a companion star, things can get interesting. If the companion is a red giant, the white dwarf's gravity can pull material off the companion. This material, mostly hydrogen and helium, falls onto the white dwarf. It accumulates on the surface. The white dwarf's mass increases. Remember the Chandrasekhar limit. A white dwarf can't exceed about 1.4 solar masses. If it does, electron degeneracy pressure can't support it. As the white dwarf approaches this limit, the pressure and temperature in its interior increase. Eventually, carbon fusion ignites in the core. But this isn't the gentle, controlled fusion of a normal star. In a white dwarf, the matter is degenerate. Pressure doesn't depend on temperature in degenerate matter. It depends only on density. So when fusion begins, the temperature rises, but the pressure doesn't increase to regulate the reaction. The fusion rate goes up. Temperature rises further. Fusion accelerates. It's a runaway reaction. Within seconds, the entire white dwarf undergoes explosive fusion. Carbon and oxygen fuse into elements like nickel and iron. The energy released is enough to completely unbind the white dwarf. It doesn't just explode. It's completely destroyed. There's no remnant left behind. The entire star is blown to pieces. Type 1, a supernovae, are incredibly important in astronomy for a specific reason. They're all remarkably similar in brightness. Because they all involve white dwarfs exploding at the same mass, the Chandrasekhar limit, they all release similar amounts of energy. They all reach similar peak brightness. This makes them standard candles. If you know the intrinsic brightness of an object, and you measure how bright it appears, you can calculate its distance. Astronomers use Type 1, a supernovae, to measure distances to far galaxies. This is how we discovered that the expansion of the universe is accelerating. In the late 1990s, two teams of astronomers observed distant Type 1, a supernovae. They measured the supernovae's brightness and calculated their distances. Then, they measured the red shifts of the host galaxies to determine how fast they're moving away from us. What they found shocked everyone. The distant supernovae were dimmer than expected. That meant they were farther away than predicted based on the galaxy's red shift. The universe wasn't just expanding. The expansion was speeding up. Galaxies are moving apart faster and faster over time. This discovery won the Nobel Prize in Physics in 2011. It led to the concept of dark energy, a mysterious form of energy that permeates space and drives the accelerating expansion. We still don't understand what dark energy is. It's one of the biggest mysteries in physics. But we discovered it thanks to Type 1, a supernovae. Let's talk about what happens to the core after a core collapse supernova. The outer layers are blown into space, but the core remains. What's left is a ball of neutrons about 20 kilometers across, a neutron star. Neutron stars are among the strangest objects in the universe. They're incredibly dense. A neutron star's mass is typically between 1.4 and 2 solar masses. All of that mass is compressed into a sphere about the size of a city. A teaspoon of neutron star material would weigh about 100 million tons, more than all the cars on Earth combined. The gravity on the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you dropped an object from 1 meter above the surface, it would hit the ground at a significant fraction of the speed of light. Neutron stars have extremely strong magnetic fields, millions to billions of times stronger than Earth's magnetic field. These magnetic fields channel radiation from the neutron star's poles. As the neutron star rotates, these beams of radiation sweep through space like lighthouse beams. If a beam happens to point toward Earth, we see a pulse of radiation every time the beam sweeps past. We call these pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She was a graduate student at Cambridge, using a radio telescope to study quasars. She noticed a strange signal. A series of pulses, incredibly regular, occurring every 1.33 seconds. At first, she and her advisor, Anthony Hewish, thought it might be a signal from an alien civilization. They jokingly called it LGM-1 for Little Green Men. But soon, they found more pulsars in other parts of the sky. The explanation became clear. These were rapidly rotating neutron stars, sending out beams of radio waves. Some pulsars rotate hundreds of times per second. The fastest known pulsar, PSR J1748, 2446 AD, rotates 716 times per second. That's a neutron star, 20 kilometers across, spinning 700 times every second. The surface is moving at about a quarter the speed of light. If it spun any faster, it would tear itself apart. Not all core collapse supernovae leave behind neutron stars. If the progenitor star was massive enough, the core might be too heavy for even neutron degeneracy pressure to support. There's a limit to how massive a neutron star can be. The exact value is uncertain, but it's probably around 2 to 2.5 solar masses. If the core mass exceeds this limit, nothing can stop the collapse. The core collapses past the neutron star stage. It keeps collapsing until it becomes a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon. Once something crosses the event horizon, it's gone. It can never come back out. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometers in radius. For a black hole with 10 solar masses, the radius would be about 30 kilometers. Black holes formed from stellar collapse are called stellar mass black holes. They're typically between 5 and a few tens of solar masses. There are also supermassive black holes at the centers of galaxies, with masses of millions to billions of solar masses. We're not entirely sure how supermassive black holes form. They might grow from stellar mass black holes that accrete matter over billions of years. Or they might form directly from the collapse of massive gas clouds in the early universe. It's an active area of research. The material blown into space by a supernova doesn't just disappear. It spreads out, forming a supernova remnant. These remnants can be spectacular. The Crab Nebula is a famous example. It's the remnant of the supernova observed in 1054. The nebula is about 11 light-years across now and still expanding at about 1,500 kilometers per second. At its center is the Crab Pulsar, rotating about 30 times per second. Another famous remnant is the Veil Nebula, part of the Cygnus Loop supernova remnant. This supernova exploded about 5,000 to 8,000 years ago. The Veil Nebula is a huge, delicate structure of glowing filaments. It's one of the most beautiful objects you can see through a telescope. Supernova remnants are important for several reasons. First, they're where new elements are injected into the interstellar medium. All the carbon, oxygen, iron, and heavier elements created in the star and the explosion get scattered into space. This enriches the interstellar medium. Eventually, this material gets incorporated into new generations of stars and planets. Second, supernova remnants are powerful sources of high-energy particles. The shock waves from supernovae accelerate particles to incredible energies. These particles, called cosmic rays, zip through the galaxy at nearly the speed of light. Some cosmic rays have energies millions of times higher than anything we can produce in particle accelerators. We're still not entirely sure how supernova remnants accelerate particles to such high energies. It involves the shock wave interacting with the interstellar magnetic field in complex ways. Third, supernova remnants can trigger the formation of new stars. The shock wave from a supernova can compress nearby gas clouds. If a cloud gets compressed enough, it can start to collapse under its own gravity. That collapse can form new stars. There's evidence that our own solar system might have been triggered by a nearby supernova. Certain isotopes, found in primitive meteorites, suggest that a supernova exploded near the gas cloud that formed our Sun about 4.6 billion years ago. The shock wave from that supernova might have compressed the cloud, triggering its collapse. If so, we owe our existence to a star that exploded billions of years ago. Let's talk about the elements created in supernovae. This is where things get really interesting from a chemistry perspective. Stars fuse light elements into heavier ones. Hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, and so on. But this fusion chain stops at iron. Iron is the end of the line for fusion in normal stellar burning. Everything heavier than iron can't be made by fusion in a star's core. Fusing iron requires energy rather than releasing it. So where do elements heavier than iron come from? Gold, silver, platinum, uranium. How are they made? The answer is supernovae. During a supernova explosion, conditions are extreme enough to create elements heavier than iron. There are two main processes: the R process and the S process. The S process, or slow process, happens during normal stellar burning. A nucleus captures a neutron. The neutron decays into a proton before the next neutron is captured. This builds up heavier elements slowly. The S process can create elements up to lead and bismuth. But the R process, the rapid process, happens in supernovae. Nuclei are bombarded with neutrons so rapidly that they capture many neutrons before any of them decay. This creates very neutron-rich isotopes. Eventually, these isotopes decay, transforming neutrons into protons and moving up the periodic table. The R process creates about half of all elements heavier than iron, including gold, platinum, and uranium. Recent observations suggest that another source might be even more important for R process elements: neutron-star mergers. When two neutron stars orbit each other, they lose energy by emitting gravitational waves. Over millions of years, their orbit shrinks. Eventually, they collide and merge. The collision is incredibly violent. It creates a brief, intense environment rich in neutrons. perfect conditions for the R process. In August 2017, we observed a neutron star merger for the first time. Gravitational wave detectors, LIGO and Virgo, detected the merger. Telescopes around the world observed the optical, infrared, and gamma-ray afterglow. Spectroscopic analysis of the light showed signatures of heavy elements being created. We literally watched gold and platinum being forged in real time. This single event might have produced several Earth masses of gold. So, when you're wearing a gold ring or necklace, the gold in it was probably created in a neutron star merger billions of years ago, scattered into space, incorporated into the gas cloud that formed our solar system, and eventually concentrated into ore deposits on Earth where humans mined it. Supernovae play a crucial role in galactic ecology. They regulate star formation. They enrich the interstellar medium with heavy elements. They heat the gas in galaxies. Without supernovae, galaxies would be very different. Star formation would proceed unchecked until all the gas was used up. There would be no heavy elements. No planets like Earth. No life. Supernovae provide negative feedback on star formation. When a massive star explodes, the blast wave heats and disperses nearby gas. This makes it harder for that gas to collapse and form new stars. It slows down star formation. But supernovae also provide positive feedback. The shock waves can trigger star formation in neighboring clouds. The result is a complex, self-regulating cycle. Star formation produces massive stars. Massive stars explode as supernovae. Supernovae, heat gas, and slow star formation. But they also enrich the gas with heavy elements and trigger new star formation in some regions. Over billions of years, this cycle enriches galaxies with heavy elements. The first stars in the universe contained only hydrogen and helium. Those were the only elements created in the Big Bang. When those first stars exploded, they enriched the interstellar medium with heavier elements. The next generation of stars formed from gas that contained carbon, oxygen, iron. Those stars created even more heavy elements when they exploded. Each generation of stars enriches the gas a little more. By the time our Sun formed, 4.6 billion years ago, the gas in our region of the galaxy contained about 2% heavy elements. That was enough to form rocky planets like Earth. Enough to eventually lead to life. Astronomers classify supernovae by their light curves and spectra. A light curve shows how the brightness changes over time. A spectrum shows what elements are present in the expanding debris. Type II supernovae show hydrogen in their spectra. They come from red supergiants that still have their hydrogen envelopes when they explode. Type 1b supernovae show helium, but no hydrogen. They come from stars that lost their hydrogen envelopes. Type 1c supernovae show neither hydrogen nor helium. They come from stars that lost both their hydrogen and helium layers. Type 1, a supernovae show silicon, but no hydrogen or helium. They come from white dwarf explosions, not core collapse. Within these categories, there are many subtypes. Type 2p supernovae have a plateau in their light curve. The brightness stays roughly constant for a few months before declining. This plateau happens because the hydrogen envelope is large and opaque. It takes a long time for the shock wave to diffuse through. Type 2L supernovae decline linearly in brightness. Type 2N supernovae show narrow lines in their spectra. The narrow lines come from interaction between the supernova ejecta and material the star shed before it exploded. These stars lost mass in powerful stellar winds years or decades before the final explosion. When the supernova shockwave hits this circumstellar material, it heats it up. The heated material emits light with narrow spectral lines. Type 2N supernovae can be extremely bright. Some are 10 to 100 times brighter than normal. Type 2 supernovae. These are called superluminous supernovae. We're still not entirely sure what powers them. One possibility is that the progenitor star shed enormous amounts of mass in the years before exploding. The supernova shockwave slams into this dense shell of material. The collision converts kinetic energy into light. Another possibility involves the neutron star left behind. If the neutron star is rotating very rapidly and has an extremely strong magnetic field, it's called a magnetar. Magnetars can emit enormous amounts of energy. This energy could power a superluminous supernova. We've observed a few supernovae that seem to be powered by magnetars. The light curves match what we'd expect if a rapidly spinning magnetar was pumping energy into the expanding debris. There's also a rare type of supernova called a pair instability supernova. These are predicted to occur in extremely massive stars. Stars with masses above about 130 solar masses. In the cores of these stars, temperatures get so high that photons have enough energy to spontaneously create electron-positron pairs. This is called pair production. Normally, photons in a star's core contribute to pressure. Radiation pressure helps support the star. But when photons create particle pairs, they disappear. Radiation pressure drops suddenly. The core loses support and collapses. The collapse triggers explosive fusion throughout the core. Unlike a normal core collapse supernova, there's no bounce. The entire core undergoes explosive fusion at once. The energy released is enormous, enough to completely destroy the star. No remnant is left behind, not even a black hole. The entire star, 100 or more solar masses, is blown to pieces. Pair instability supernovae are thought to have been common in the early universe, when the first generation of stars formed. Those stars, called population 3 stars, contained no heavy elements, only hydrogen and helium. Without heavy elements, stars can grow much more massive before radiation pressure limits their growth. Some population 3 stars might have reached 500 solar masses or more. Many of those would have ended as pair instability supernovae. We haven't definitively observed a pair instability supernova yet, but we've seen a few candidates. Superluminous supernovae with properties that match predictions for pair instability explosions. Supernovae are also important for understanding the history of the universe. By observing distant supernovae, we can look back in time. Light from a supernova, 10 billion light-years away, took 10 billion years to reach us. We're seeing that supernova as it was 10 billion years ago, when the universe was only about a quarter of its current age. By studying how supernova rates have changed over cosmic time, we learn about the history of star formation. When were stars forming most rapidly? When did the rate slow down? 2. How has the chemical composition of stars changed over time. Supernovae in distant galaxies also tell us about the expansion of the universe. Type 1, a supernovae, being standard candles, let us measure distances to far galaxies. Combine those distances with measurements of how fast the galaxies are receding, and we can trace the expansion history of the universe. This is how we discovered dark energy. We're now using supernovae to measure the expansion rate with increasing precision. There's currently a tension in cosmology. Different methods of measuring the expansion rate give slightly different answers. Measurements based on nearby supernovae give one value. Measurements based on the cosmic microwave background give a slightly different value. This discrepancy, called the Hubble tension, is one of the biggest puzzles in cosmology. It might point to new physics, or it might indicate systematic errors in one or both measurements. We're not sure yet. But supernovae are key to resolving this mystery. Detecting supernovae is a major effort in modern astronomy. Automated surveys scan the sky every night, looking for new, bright objects. The Zwicky Transient Facility, for example, scans the entire visible sky every few nights. It detects hundreds of supernovae per year. Other surveys include ATLAS, the all-sky automated survey for supernovae, and the upcoming Vera-Rubin Observatory. When a supernova is detected, alerts go out to astronomers around the world. Follow-up observations begin immediately. Spectra are taken to classify the supernova. Light curves are measured to track how the brightness changes. Different wavelengths are observed: optical, infrared, ultraviolet, X-ray. Each wavelength reveals different physics. For nearby supernovae, we can learn an enormous amount. SN 1987A, the supernova in the Large Magellanic Cloud, was one of the most studied objects in the history of astronomy. It was the closest supernova observed since the invention of the telescope, only about 168,000 light-years away. Astronomers observed it across the entire electromagnetic spectrum. They detected neutrinos from the core collapse. On February 23, 1987, neutrino detectors in Japan and the United States detected a burst of neutrinos. About 20 neutrinos total over a period of 13 seconds. That might not sound like much, but neutrinos almost never interact with matter. Trillions of neutrinos from the sun pass through your body every second. You never notice them. Detecting 20 neutrinos from a supernova 168,000 light-years away was extraordinary. It confirmed our theoretical understanding of core collapse. The neutrinos arrived about 3 hours before the light. That makes sense. The neutrinos were produced when the core collapsed. They escaped almost immediately, traveling at the speed of light. The light was produced when the shock wave reached the surface. That took 3 hours. The neutrinos gave us a heads up. They told us the core had collapsed 3 hours before the explosion became visible. SN 1987 A also taught us about the progenitor star. Before the explosion, astronomers had images of that region of the Large Magellanic Cloud. After the supernova, they went back and looked at those old images. They identified which star had exploded. It was a blue supergiant called Sandulique, -69°, 202. This was a surprise. Astronomers expected massive stars to become red supergiants before exploding. Sandulique was blue. indicating a hotter surface temperature. This told us that not all massive stars follow the same evolutionary path. Some remain blue supergiants right up to the end. We're still refining our models to understand why. The remnant of SN 1987A has been studied intensely ever since. We've watched the supernova ejector expand. We've seen the debris slam into a ring of material surrounding the star. That ring was shed by the star thousands of years before it exploded. When the supernova shock wave hit the ring, it lit up. Hot spots appeared around the ring as the shock heated the gas. Over the years, these hot spots have evolved. Some have faded. Others have brightened. We're watching the supernova remnant form in real time. At the center of the remnant, there should be a neutron star or black hole. We haven't detected it yet. The remnant is too bright and too young. The pulsar, if it exists, is hidden in the glare of the expanding debris. But in a few more decades, the remnant will fade. We might then detect the neutron star. If we do, it will be one of the youngest known neutron stars. If we don't, it might mean a black hole formed instead. Either way, it will tell us about the final fate of massive stars. Supernovae can also affect life on Earth. If a supernova explodes too close, it could be dangerous. The high-energy radiation and cosmic rays from a nearby supernova could damage Earth's ozone layer. Without the ozone layer, harmful ultraviolet radiation from the sun would reach the surface. This could cause mass extinctions. There's some evidence that a supernova might have contributed to one of Earth's past mass extinctions. Around 2.6 million years ago, there were elevated levels of iron-60 in ocean sediments. Iron-60 is a radioactive isotope that's produced in supernovae. It doesn't occur naturally on Earth. Finding it in sediments suggests that material from a supernova reached Earth around that time. A supernova, about 300 light-years away, could have deposited that iron-60. At that time, Earth was transitioning from the Pliocene to the Pleistocene epoch. Some megafauna went extinct. The climate was changing. It's hard to say whether the supernova played a role. But it's an intriguing possibility. For a supernova to be truly dangerous, it would need to be within about 30 light-years. Luckily, there are no stars that massive that close to us. The nearest candidate for a future supernova is Betelgeuse, about 550 light-years away. Betelgeuse is a red supergiant nearing the end of its life. It could explode any time in the next 100,000 years. Or it might have already exploded, and the light just hasn't reached us yet. When it does explode, it will be spectacular. Visible during the day, as bright as the moon at night. But it's far enough away that it won't harm Earth. Betelgeuse has been in the news recently because it dimmed dramatically in late 2019 and early 2020. Its brightness dropped to about 40% of normal. Some people speculated it might be about to explode, but the dimming was likely caused by dust. Red supergiants shed mass in powerful stellar winds. Sometimes, a particularly dense clump of dust forms. The dust blocks some of the star's light. The star appears dimmer. Eventually, the dust disperses. The brightness returns to normal. That's what happened with Betelgeuse. By mid-2020, it had brightened again. We don't know when Betelgeuse will explode. It could be tomorrow. It could be in 100,000 years. When it does, astronomers will be ready. Telescopes will observe it continuously. We'll learn more from that one supernova than from thousands of distant ones. Another star to watch is Eta Carinae, about 7,500 light-years away. Eta Carinae is one of the most massive stars known, between 100 and 150 solar masses. It's incredibly unstable. In the mid-1800s, it underwent a massive eruption. It became one of the brightest stars in the sky for a few years. This eruption, called the Great Eruption, ejected several solar masses of material. That material now forms the homunculus nebula around the star. Eta Carinae is probably nearing the end of its life. It could explode as a supernova sometime in the next million years. Or it might undergo more eruptions first. We're not sure. But it's one of the most fascinating stars in the galaxy. Supernovae represent the ultimate transformation. A star, stable for millions of years, burning fuel in its core, supporting itself against gravity. Then, in less than a second, the core collapses. The star explodes. Everything changes. The star that dies. What's left is either a neutron star or a black hole. The outer layers, containing all the elements the star created during its life, are scattered into space. Those elements will eventually become part of new stars, new planets, perhaps new life. Every atom in your body, heavier than hydrogen, was created in a star. Most of those atoms were scattered into space when that star exploded. The iron in your blood, the calcium in your bones, the oxygen you're breathing. All of it came from supernovae. You are, quite literally, made of star stuff. That's not poetic exaggeration. It's scientific fact. Supernovae also represent the universe's way of recycling material. Stars form from clouds of gas. They burn that gas, fusing it into heavier elements. They return it to space when they explode. The gas mixes with the interstellar medium. New stars form. The cycle continues. Each generation of stars is slightly richer in heavy elements than the last. The first stars in the universe contained no heavy elements. When they exploded, they enriched the gas with carbon, oxygen, iron. The next generation of stars formed from that enriched gas. When they exploded, they added even more heavy elements. Over billions of years, the universe has become progressively enriched. Our Sun is a third-generation star, maybe fourth. It contains about 2% heavy elements. That was enough to form rocky planets, enough to eventually lead to us. Let's dive deeper into the physics of the core collapse itself. This is where things get truly extreme. The collapse of an iron core happens faster than almost anything else in nature. The core starts at roughly the size of Earth, about 12,000 kilometers across. Within a quarter of a second, it shrinks to about 20 kilometers. That's a reduction in radius by a factor of 600. The volume shrinks by a factor of 200 million, all in a fraction of a second. To put this in perspective, imagine Earth shrinking to the size of a small city in less time than it takes to blink. Every point in the core is falling inward at roughly a quarter the speed of light, about 75,000 kilometers per second. Nothing in our everyday experience moves that fast. The core is in free fall. and nothing can stop it until it reaches nuclear densities. The energy released during this collapse is staggering. Most of that energy goes into neutrinos, about 3 times 10 to the 53rd power ergs. That's 3, followed by 53 zeros. In more familiar units, that's about 200 times the energy the Sun will radiate in its entire 10 billion year lifetime, released in seconds. 99% of that energy is carried away by neutrinos. Only 1% goes into the kinetic energy of the explosion. The light we see, the blast wave, all of that is powered by just 1% of the total energy. The neutrinos carry the rest away, streaming out through the star at the speed of light. Most of them escape into space without interacting with anything. They carry information about the core collapse with them. If we could detect all the neutrinos from a nearby supernova, we'd learn everything about what happened in the core. Unfortunately, neutrinos are extraordinarily hard to detect. Current neutrino detectors can catch maybe a few dozen neutrinos from a nearby supernova. That's enough to confirm our basic understanding. But it's a tiny fraction of the total number emitted. The neutron star left behind after the collapse is an object of almost incomprehensible extremes. Let's explore what conditions are like on a neutron star. The surface gravity is about 400 billion times Earth's gravity. If you were standing on a neutron star, which you couldn't because you'd be instantly crushed, you would weigh about 40 billion times more than you do on Earth. If you weigh 70 kilograms on Earth, you'd weigh about 3 trillion kilograms on a neutron star, more than the mass of Mount Everest. The escape velocity from a neutron star's surface is about half the speed of light, 150,000 kilometers per second. That means anything leaving the surface needs to reach half-light speed just to escape. The surface temperature of a young neutron star is around 1 million degrees. That's about 200 times hotter than the surface of the Sun. Even after cooling for thousands of years, neutron stars remain at tens of thousands of degrees. The atmosphere of a neutron star is only a few centimeters thick. All the gas is crushed into an incredibly thin layer by the intense gravity. Below the atmosphere is the crust. The crust is made of atomic nuclei crushed together in a crystalline lattice. It's extraordinarily dense. A sugar cube-sized piece of neutron star crust would weigh about 100 million tons, more than all the humans on Earth combined. The crust is also the strongest material in the universe. It's billions of times stronger than steel. It has to be to withstand the enormous gravitational forces trying to crush it. Deep in the crust, the nuclei become increasingly neutron-rich. Normal atomic nuclei have roughly equal numbers of protons and neutrons. But, under the extreme pressure in a neutron star's crust, nuclei with far more neutrons than protons become stable. At the bottom of the crust, neutrons start to drip out of the nuclei. This region is called the neutron drip line. Below the crust is the outer core. Here, matter is mostly free neutrons with a small fraction of protons and electrons. It's a superfluid, a fluid with zero viscosity that flows without friction. The neutrons pair up in a quantum mechanical state similar to the electron pairs in superconductors. This superfluid has strange properties. It can flow through tiny spaces without resistance. It forms quantized vortices, little whirlpools of rotating superfluid. The inner core is even stranger. We're not entirely sure what happens there. The pressure and density are so extreme that our understanding of physics becomes uncertain. Matter might exist in exotic states. Perhaps pion condensates or kaon condensates, states where particles called pions or kaons form a quantum condensate. Or maybe quark matter, where the neutrons themselves break down into their constituent quarks. Under normal conditions, quarks are always confined inside protons and neutrons. You can't isolate a single quark. But at the extreme densities in a neutron star's core, quarks might become deconfined. They'd form a quark-gluon plasma, a soup of free quarks and gluons. If this happens, the core of the neutron star would essentially be one giant atomic nucleus, not made of neutrons, but of quarks. This hypothetical object is called a quark star. We don't know if quark stars exist. We don't even know if quark matter forms in neutron star cores. The physics at these densities is beyond what we can test in laboratories. But it's possible. And if quark stars do exist, they'd be even denser than neutron stars. Neutron stars also have the strongest magnetic fields in the universe. Typical neutron stars have magnetic fields about 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have fields 1,000 times stronger than that. A magnetar's magnetic field is about 10 to the 15th power times Earth's field. That's a 1, followed by 15 zeros. These magnetic fields are so strong, they affect the vacuum of space itself. In a strong magnetic field, virtual particle-antiparticle pairs in the vacuum become polarized. This changes the properties of light passing through the field. Photons can split into multiple photons, or merge together. The vacuum itself becomes birefringent, like a crystal, bending light differently depending on its polarization. These effects have been observed in light from magnetars. The magnetic field also affects the structure of atoms. In a field of 10 to the 12th power, Gauss atoms become elongated into cigar shapes. The electron orbitals stretch out along the magnetic field lines. Chemistry as we know it breaks down completely. At 10 to the 15th power Gauss, the field energy dominates over atomic binding energy. Atoms can't exist at all. Pulsars, rotating neutron stars, are natural laboratories for extreme physics. The rotation provides a clock of incredible precision. Some millisecond pulsars keep time better than atomic clocks. The fastest known pulsar rotates 716 times per second. At the equator, the surface is moving at about 24% the speed of light. If it rotated any faster, the centrifugal force would tear it apart. The rotation gradually slows down as the pulsar loses energy. That energy goes into accelerating particles in the pulsar's magnetosphere. The slowing rate tells us about the pulsar's magnetic field strength and the physics of the magnetosphere. By timing pulsar pulses very precisely, we can detect tiny changes in the rotation rate. These changes reveal glitches, sudden spin-ups when the superfluid in the core adjusts and transfers angular momentum to the crust. Pulsar timing also lets us detect gravitational waves. As gravitational waves pass through space between Earth and a pulsar, they stretch and compress space. This causes tiny timing variations in the pulsar signals. By monitoring an array of pulsars, we can detect gravitational waves with wavelengths of light years. This technique has already detected gravitational wave background from supermassive black hole mergers across the universe. Let's talk about the different types of supernovae in more detail. I mentioned earlier that there are several types. Let's explore what distinguishes them. Type 1. A supernovae come from white dwarfs. But not all white dwarfs explode. You need specific conditions. The white dwarf must be in a binary system. Its companion must be transferring mass to it. And the white dwarf's mass must approach the Chandrasekhar limit. There are two main scenarios for how this happens. The single degenerate scenario involves a white dwarf accreting material from a normal companion star. The companion might be a red giant or a main sequence star. As the companion evolves and expands, material spills over onto the white dwarf. Over millions of years, the white dwarf's mass increases. When it reaches about 1.4 solar masses, it explodes. The double degenerate scenario involves two white dwarfs orbiting each other. They lose energy by emitting gravitational waves. Their orbit shrinks. Eventually, they merge. If their combined mass exceeds the Chandrasekhar limit, the merger triggers a Type 1, a supernova. We're not entirely sure which scenario is more common. Both probably occur. Different Type 1, a supernovae, might come from different channels. Recent observations have found that not all Type 1, a supernovae, are exactly the same brightness. There's a relationship between peak brightness and how fast the light curve declines. Brighter supernovae fade more slowly. Dimmer ones fade faster. This Phillips relationship, discovered in the 1990s, lets us use Type 1, a supernovae, as even better standard candles. We measure how fast the light fades and use that to determine the intrinsic brightness. Then, we compare that to the observed brightness to calculate distance. Type 2 supernovae come in many flavors. The classic Type 2P, with a plateau in the light curve, comes from a red supergiant. The plateau forms because the hydrogen envelope is extended and opaque. The shock wave has to diffuse through this thick envelope. That takes time. During the plateau phase, the supernova maintains roughly constant brightness as the envelope expands and cools. Eventually, the envelope becomes transparent. The plateau ends. The light curve starts declining more rapidly, powered now by radioactive decay. Type 2L, supernovae, decline linearly, without a plateau. These might come from supergiants with less massive envelopes. The envelope is thinner, so there's no extended plateau phase. Type 2N supernovae are fascinating. The N stands for narrow, referring to narrow lines in the spectrum. These narrow lines indicate that the supernova ejector is slamming into dense circumstellar material the star shed before exploding. Some Type 2N supernova are extraordinarily bright. They can be 10 to 100 times brighter than normal Type 2 supernovae. The extra brightness comes from the collision between the ejector and the circumstellar material. Kinetic energy gets converted into radiation. These supernovae tell us that some massive stars undergo dramatic mass loss in the years or decades before exploding. We're not entirely sure what causes this mass loss. Maybe violent instabilities in the star's envelope. Maybe interactions with a binary companion. It's an active area of research. Type 1b and IC supernovae are core collapse events from massive stars that lost their hydrogen envelopes. Type 1b shows helium in the spectrum. Type 1c shows neither hydrogen nor helium. These stripped envelope supernovae are thought to come from very massive stars. Stars massive enough that their stellar winds were strong enough to blow away the outer layers. Or stars in binary systems where the companions stripped away the envelope. Wolf-Rayet stars are likely progenitors of Type 1b and IC supernovae. Wolf-Rayet stars are extremely massive and extremely hot. They have powerful stellar winds that blow away several solar masses of material over their lifetimes. By the time they explode, they've lost most or all of their hydrogen envelope. Some Type 1c supernovae are associated with long-duration gamma-ray bursts. These are among the most energetic explosions in the universe. A gamma-ray burst releases more energy in seconds than the Sun will emit in its entire lifetime. The connection between Type 1c supernovae and gamma-ray bursts suggests that some core collapses produce jets. Focused beams of material moving at relativistic speeds. If the jet points toward Earth, we see a gamma-ray burst. If it points away, we just see a regular supernova. The mechanism for producing these jets is still debated. It might involve a rapidly rotating black hole or magnetar formed in the core. The rotation and strong magnetic fields might launch jets perpendicular to the rotation axis. Superluminous supernovae are a class of extremely bright supernovae discovered in the past 2 decades. They're 10 to 100 times brighter than normal supernovae. Peak luminosities can exceed 10 to the 44th power ergs per second. That's brighter than an entire galaxy. We're still trying to understand what powers them. Several mechanisms have been proposed. One possibility is the magnetar model. If the core collapse produces a magnetar with an extremely strong magnetic field and rapid rotation, it can pump enormous amounts of energy into the expanding ejector. The magnetar acts like a central engine, powering the supernova from the inside. Another possibility is pair instability supernovae. Stars with masses between about 130 and 250 solar masses can undergo pair instability. The entire star is destroyed in the explosion. No remnant is left behind. The energy released is enormous, potentially explaining superluminous supernovae. A third possibility is interaction with dense circumstellar material. If the progenitor star shed enormous amounts of mass just before exploding, the supernova ejector would collide with this material. The collision converts kinetic energy into light. This is similar to Type 2n supernovae, but on a much more extreme scale. The diversity of supernovae tells us that massive star evolution is complex. Not all massive stars follow the same path. Rotation matters. A rapidly rotating star evolves differently from a slowly rotating one. Metallicity matters. 2010. Stars with more heavy elements have stronger stellar winds. They lose more mass over their lifetimes. Binary interactions matter. A star in a close binary system can have its envelope stripped by its companion, or it can accrete mass from the companion, changing its evolution. Magnetic fields matter. Strong magnetic fields can affect stellar structure and mass loss. All these factors combine to produce the rich variety of supernovae we observe. Let's talk about supernova cosmology in more detail. In the 1990s, 2 independent research teams set out to measure the expansion history of the universe. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams used the same strategy. Find distant Type 1, a supernovae. Measure their distances using their brightness. Measure their redshifts to determine how fast they're receding. Compare the distances and recession velocities to previous models of cosmic expansion. The expectation was that the expansion would be slowing down. Gravity pulls galaxies together. That should slow the expansion. The question was how much? Is the universe dense enough that gravity will eventually stop the expansion and reverse it, causing a big crunch? Or is it not dense enough, and will it expand forever? Both teams observed dozens of distant type 1, a supernovae. Supernovae at redshifts of 0.5 to 1. That means, looking back in time, about 5 to 8 billion years. What they found shocked everyone. The distant supernovae were dimmer than expected. That meant they were farther away than predicted. The universe wasn't slowing down. It was speeding up. The expansion was accelerating. At first, people thought there must be errors. Maybe dust was dimming the distant supernovae. But dust also reddens light, and the colors of the supernovae didn't show significant reddening. Maybe distant supernovae are intrinsically dimmer than nearby ones. But there was no reason to expect that, and follow-up studies found no systematic differences. The result held up. The expansion is accelerating. This discovery won the Nobel Prize in Physics in 2011. But it raised a profound question. What's causing the acceleration? Gravity is attractive. It should slow expansion, not speed it up. To explain accelerating expansion, you need something that acts like a repulsive force. Physicists call this dark energy. Dark energy is the name we give to whatever is causing the acceleration. But we don't actually know what it is. The simplest explanation is that dark energy is the cosmological constant. Einstein introduced the cosmological constant in 1917. He was trying to find a solution to his general relativity equations that described a static universe. The universe wasn't expanding or contracting. To achieve this, he added a constant term to his equations. A term representing a uniform energy density of empty space itself. When it was discovered that the universe is expanding, Einstein called the cosmological constant his biggest blunder. But it turns out it might not have been a blunder after all. If the cosmological constant exists, it represents vacuum energy, energy inherent to space itself. Even empty space, devoid of matter and radiation, has energy. This vacuum energy has a peculiar property. Its pressure is negative. Negative pressure acts like a repulsive force in general relativity. It causes space to expand faster and faster. The problem is that when you try to calculate the cosmological constant from quantum field theory, you get an answer that's about 10 to the 120th power times larger than observed. That's the worst prediction in the history of physics. Clearly, something is missing from our understanding. Maybe dark energy isn't the cosmological constant. Maybe it's a dynamical field that changes over time. Physicists call this quintessence. Or maybe general relativity needs to be modified on cosmological scales. We don't know. Dark energy remains one of the deepest mysteries in physics, and we discovered it through supernovae. Supernovae continue to play a crucial role in measuring the expansion rate of the universe. The Hubble constant, which describes how fast the universe is expanding right now, can be measured in different ways. One way uses the cosmic microwave background. We measure tiny temperature fluctuations in the afterglow of the Big Bang. Those fluctuations encode information about the universe's composition and expansion rate. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. Another way uses the cosmic distance ladder. We start with nearby distance measurements, parallaxes for nearby stars, Cepheid variable stars in nearby galaxies. Then we use those Cepheids to calibrate. Type 1, a supernova. Finally, we use Type 1, a supernovae, in distant galaxies to measure the Hubble constant. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. Those two numbers don't agree. The difference is about 8%. That might not sound like much, but it's statistically significant. Both measurements are very precise. They shouldn't disagree this much. This discrepancy is called the Hubble tension. It's one of the biggest unsolved problems in cosmology. Either there's some systematic error in one or both measurements, or there's new physics we don't understand. Maybe dark energy isn't constant. Maybe it's changing over time. Maybe there's another component to the universe's energy budget that we haven't accounted for. Maybe the universe's expansion has varied in unexpected ways. Resolving the Hubble tension is a major goal of current astronomy. And supernovae are key to that effort. Let's return to the question of what determines whether a core collapse leaves a neutron star or a black hole. This is still an area of active research. The naive answer is that it depends on the mass of the iron core. If the core is less than about 2 to 2.5 solar masses, it becomes a neutron star. If it's heavier, it collapses to a black hole. But the reality is more complicated. The explosion mechanism matters. If the neutrino-driven explosion is successful and blows off most of the star's mass, even a heavy core might leave behind a neutron star. If the explosion fails or is weak, more material can fall back onto the core after the initial collapse. This fallback can push the remnant over the limit. The neutron star that initially formed collapses further into a black hole. We've observed what might be examples of this. Some supernovae produce very little radioactive nickel. That suggests that most of the material fell back onto the core instead of being ejected. These failed or weak explosions might produce black holes. The most massive stars, above about 25 to 30 solar masses, might not produce successful explosions at all. The core is so massive that the neutrino-driven mechanism can't revive the shock. The collapse continues directly to a black hole. The outer layers fall onto the collapsing core. From the outside, you might not see a supernova at all. The star just disappears. Or you might see a weak transient as some material is ejected in the early stages before everything falls back. There's evidence for such failed supernovae. Astronomers have observed red supergiants that suddenly disappeared without producing a bright supernova. These might be direct core collapse to black holes. The relationship between supernova type and progenitor mass is roughly as follows. Stars between 8 and about 15 solar masses produce neutron stars. They undergo successful core collapse supernovae, usually type 2p with hydrogen envelopes intact. Stars between 15 and 25 solar masses also produce neutron stars, but the explosions might be weaker. Some might produce type 2L or stripped envelope supernovae if they've lost part of their envelopes. Stars between 25 and 40 solar masses might produce black holes. The core is massive enough that neutrino-driven explosions struggle. Many might fail or be weak, with significant fallback. Stars above 40 solar masses likely collapse directly to black holes. The explosions fail completely. Little to no material is ejected. But this is a rough guide. Individual cases can vary enormously depending on rotation, metallicity, and binary interactions. Now let's discuss how supernovae affect galaxy evolution. Galaxies aren't just collections of stars. They contain gas, which is the raw material for forming new stars. Supernovae inject energy into this gas. Each supernova releases about 10 to the 51st power ergs of kinetic energy. That energy goes into the expanding supernova remnant. The remnant sweeps up gas from the interstellar medium. It creates a bubble of hot, low-density gas. If many supernovae occur in the same region, their bubbles overlap. This creates a superbubble, a huge cavity filled with hot gas. The hot gas can expand outward, breaking through the disk of the galaxy. This creates a galactic wind. Gas flows out of the galaxy, driven by the pressure from supernova explosions. Galactic winds remove gas from galaxies. This reduces the rate of star formation. It's a form of negative feedback. Stars form. The most massive ones explode. The explosions heat and expel gas that slows down further star formation. Without this feedback, galaxies would convert all their gas into stars very quickly. Within a few 100 million years, there'd be no gas left. But we observe galaxies with plenty of gas. They're still forming stars billions of years after they formed. Supernova feedback is part of why. It regulates star formation, spreading it out over billions of years. Supernova feedback is also important for preventing the centers of galaxies from forming too many stars. Gas naturally flows toward the center of a galaxy. If left unchecked, the center would become extremely dense with stars. But supernovae in the central regions heat the gas. That pressure can drive the gas outward. This helps maintain a more spread-out distribution of stars. Supernovae also enrich the interstellar medium with metals. In astronomy, any element heavier than helium is called a metal. Carbon, nitrogen, oxygen, iron, everything. The first stars in the universe had no metals. They formed from primordial gas, just hydrogen and helium from the Big Bang. When those stars exploded, they enriched the surrounding gas with metals. The next generation of stars formed from gas that contained a small amount of metals. Those stars produced more metals when they exploded. Each generation increases the metallicity of the interstellar medium. We can trace this enrichment history by looking at stars of different ages. Old stars, formed billions of years ago, have low metallicity. Young stars, formed recently, have higher metallicity. Our Sun has about 2% metals by mass. That's fairly high, but not the highest. Some very young stars in regions of active star formation have even higher metallicity. Metallicity affects how stars evolve. High metallicity stars have stronger stellar winds. They lose more mass over their lifetimes. That changes their final fate. A high metallicity star might end up as a stripped envelope supernova because its winds blew away the hydrogen envelope. A low metallicity star of the same initial mass might retain its envelope, and explode as a Type 2P supernova. Metallicity also affects planet formation. Rocky planets need metals: silicon, iron, magnesium, oxygen. You can't build an Earth without them. The first generation of stars couldn't have rocky planets. There weren't enough metals. By the time our Sun formed, 4.6 billion years ago, the metallicity was high enough to form rocky planets. That's why Earth exists. The chemical composition of the interstellar medium also affects star formation itself. Metals are crucial for cooling gas. When a gas cloud collapses to form stars, it heats up. The heat generates pressure that resists collapse. For the collapse to continue, the cloud needs to cool down. Radiation carries away the heat. But pure hydrogen and helium are inefficient radiators. They don't radiate much at the temperatures typical of collapsing clouds. Metals are much better radiators. Carbon and oxygen radiate efficiently through molecular lines. That helps the gas cool faster. Faster cooling means the cloud can fragment into smaller pieces. Each fragment becomes a star. With metals, you get more fragmentation and more low-mass stars. Without metals, fragmentation is less efficient. You get fewer, more massive stars. The first stars in the universe were probably very massive. Some might have been hundreds of solar masses. Modern stars span a much wider range of masses, from brown dwarfs less than a tenth of a solar mass to massive stars over 100 solar masses. This change in the distribution of stellar masses is partly due to increasing metallicity from supernovae. Supernovae also produce cosmic rays. Cosmic rays are high-energy particles, mostly protons, traveling through space at nearly the speed of light. They bombard Earth constantly. About 1 cosmic ray particle hits every square centimeter of Earth's atmosphere every second. When they hit the atmosphere, they create showers of secondary particles: muons, pions, electrons, photons. Some of these particles reach the ground. You're being hit by cosmic ray secondaries right now. Most cosmic rays come from supernova remnants. The shock waves from supernovae accelerate particles. Exactly how this works is still being researched. It involves a process called diffusive shock acceleration. Particles cross back and forth across the shock wave. Each crossing, they gain energy. Do this enough times, and they reach very high energies. Some cosmic rays have energies over 10 to the 20th power electron volts. That's about the kinetic energy of a baseball traveling at 90 kilometers per hour, all in a single proton. These ultra-high-energy cosmic rays probably don't come from supernovae. They might come from active galactic nuclei or other exotic sources. But the majority of cosmic rays, those below 10 to the 15th power electron volts, are likely from supernova remnants. Cosmic rays play an important role in the galaxy. They ionize gas in molecular clouds. That affects the chemistry and the magnetic field structure. They provide pressure that helps support gas against gravity. They contribute to heating the interstellar medium. All of this affects star formation and the structure of the galaxy. Supernovae can also trigger star formation, not just suppress it. The shock wave from a supernova compresses nearby gas clouds. If a cloud is already close to collapsing, the compression can push it over the edge. The cloud begins collapsing and forming stars. There's evidence that star formation often occurs in supershells and superbubbles, created by previous generations of supernovae. The shells of compressed gas around the bubbles are sites of active star formation. This creates a cycle. Stars form, massive stars explode, the explosions compress nearby gas, new stars form, and the cycle continues. This is called triggered or sequential star formation. It might explain why stars tend to form in groups and associations rather than uniformly throughout the galaxy. There's even evidence that our own solar system's formation was triggered by a nearby supernova. Some meteorites contain daughter products of short-lived radioactive isotopes. Aluminum-26, for example. Aluminum-26 has a half-life of only 700,000 years. That's very short compared to the age of the solar system. For it to be present when the solar system formed, it must have been produced shortly before. Supernovae produce aluminum-26. One interpretation is that a supernova exploded near the molecular cloud that was forming our sun. The shock wave compressed the cloud, triggering its collapse. And the debris from the supernova, including aluminum-26, was incorporated into the forming solar system. If this is true, we owe our existence to that supernova. Without it, the cloud might have taken much longer to collapse, or might never have collapsed at all. We've talked about supernovae as individual events, but it's worth considering them in the broader context of stellar populations. In a typical galaxy, there are millions to billions of stars. At any given time, some of those stars are massive enough to eventually become supernovae. The supernova rate in a galaxy depends on the star formation rate. More star formation means more massive stars. More massive stars means more supernovae. In a galaxy like the Milky Way, with a moderate star formation rate, the supernova rate is about 1 to 2 per century. In starburst galaxies, where star formation is very rapid, the supernova rate can be much higher. Dozens per century. Even one per year in the most extreme cases. Over a galaxy's lifetime, billions of years, that adds up to millions or billions of supernovae. Each one injecting energy and metals into the interstellar medium. Each one affecting the galaxy's evolution. The cumulative effect is enormous. Supernovae have fundamentally shaped the galaxies we see today. Let's explore some of the most famous historical supernovae in more detail. The supernova of 185 CE is the earliest recorded in history. Chinese astronomers documented it in the Book of Later Han. They described a guest star appearing in the southern sky. It remained visible for about 8 months. The remnant of this supernova, called RCW86, has been identified. It's a faint shell of expanding gas about 8,000 light-years away. The supernova of 393 CE was recorded by Chinese astronomers. It appeared in the constellation Scorpius. They described it as being as large as half a bamboo mat. That suggests it was quite bright, possibly visible during the day. The remnant might be SNRG 347.30.5, though the identification is uncertain. In 1006, a supernova appeared in the constellation Lupus. This was one of the brightest stellar events ever recorded. Chinese, Japanese, Arab, and European astronomers all documented it. At its peak, it was bright enough to cast shadows at night. It was visible for over 2 years. The remnant, SNRG 327.614.6, is one of the brightest supernova remnants in the sky at high energies. SN 1054, which created the Crab Nebula, was observed by Chinese and Arab astronomers. There's debate about whether European astronomers recorded it. If they did, their records haven't survived. The supernova was visible in daylight for 23 days. At night, it remained visible to the naked eye for about 653 days, almost 2 years. The Crab Nebula is now one of the most studied objects in astronomy. It was the first astronomical object identified as a supernova remnant. In the 1940s, astronomers realized that the nebula was expanding. By measuring the expansion rate and working backward, they calculated that the explosion occurred around 1054, matching the historical records. At the center of the Crab Nebula is the Crab pulsar. It rotates about 30 times per second. The pulsar was discovered in 1968, shortly after the first pulsars were found. It was the first pulsar to be identified with a supernova remnant. That confirmed the theory that pulsars are rotating neutron stars formed in supernova explosions. The Crab pulsar is slowing down as it loses energy. That energy goes into accelerating particles in the surrounding nebula. The nebula glows from X-rays to radio waves, powered by this pulsar wind. In 1181, a supernova appeared in the constellation Cassiopeia. Chinese and Japanese astronomers recorded it. It was visible for about 6 months. The remnant is known as 3C58. It's a bright radio source. The supernova of 1572, observed by Tycho Brahe, appeared in Cassiopeia. Tycho was 26 years old at the time. He observed the supernova carefully, measuring its position over many months. He showed that it had no parallax. That meant it was far beyond the moon. It was a true star, appearing in the supposedly unchanging celestial sphere. This challenged Aristotelian cosmology. The supernova reached magnitude -4, brighter than Venus. It was visible during the day for several weeks. It remained visible to the naked eye for about 16 months. Modern observations show that Tycho's supernova was a Type 1a, a white dwarf explosion. The remnant is expanding at about 9,000 kilometers per second. Studies of the remnant have taught us a lot about Type 1a explosion mechanisms. Johannes Kepler observed a supernova in 1604. This was the last supernova observed in the Milky Way, over 400 years ago. The supernova appeared in the constellation Ophiuchus. It reached magnitude -2.5, rivaling Jupiter in brightness. Kepler studied it intensely. He wrote a book about it, De Stella Nova, on the new star. The supernova was also observed in China, Korea, and the Middle East. It remained visible for about 1 year. Kepler's supernova was also a Type 1a. The remnant is being studied with modern telescopes. X-ray observations reveal the structure of the expanding debris. We can see different elements distributed in clumps. That tells us about the explosion mechanism, how the white dwarf was destroyed. Cassiopeia A, or Cass A, is another famous supernova remnant. The supernova occurred around 1680, give or take a decade. Oddly, there are no confirmed historical records of anyone observing it. It should have been visible. Estimates suggest it would have reached magnitude 6. That's right at the limit of naked eye visibility. Maybe the sky was cloudy. Maybe no one happened to be looking in that direction. Or maybe someone did observe it, but their records were lost. there is one possible observation. John Flamsteed, the first Astronomer Royal of England, recorded a star in the position of Cas A in 1680. He catalogued it as 3 Cassiopeiae. Later, the star disappeared. It's possible that Flamsteed saw the supernova when it was fading. Cas A is now one of the brightest radio sources in the sky. It's a powerful X-ray source. The remnant is expanding at about 7,500 kilometers per second. At the center, there's a neutron star. It's one of the youngest known neutron stars, only about 340 years old. It's cooling rapidly. Observations over the past decade show its temperature dropping faster than expected. This tells us about the interior structure of neutron stars, how heat is transported, what the matter is made of. Cas A has taught us an enormous amount about supernova physics. Since the invention of the telescope, no supernova has been observed in the Milky Way. That's statistically unusual. We should have seen 1 or 2 by now. Maybe they occurred on the far side of the galaxy, hidden by dust. Or maybe we've just been unlucky. The next one could happen any time. Astronomers are watching. Amateur astronomers regularly scan the sky, looking for novae and supernovae in nearby galaxies. Automated surveys monitor millions of stars. When the next Milky Way supernova occurs, we'll know within hours. Outside our galaxy, we've observed thousands of supernovae. Each one teaches us something. Some supernovae are peculiar, not fitting neatly into standard classifications. SN 2006 G was one of the most luminous supernovae ever observed. It reached an absolute magnitude of -21. That's about 100 times brighter than a typical Type 1, a supernova. It shone with the light of 100 billion suns. We're still not entirely sure what powered it. One possibility is a pair instability supernova. Another is a normal core collapse supernova with extreme interaction with circumstellar material. SN 2009 IP was even brighter. Absolute magnitude of about -22.5. It was discovered by amateur astronomer Robert McNaught in a galaxy about 1.6 billion light-years away. The light curve and spectrum were unusual. It didn't fit standard models. It might have been powered by a magnetar, or perhaps it was a very massive star undergoing pair instability. SN 2014 J appeared in the nearby galaxy M82. It was a Type 1, a supernova. What made it special was its proximity, only about 11.4 million light-years away. That's very close for a supernova. It became bright enough to be visible through small telescopes. Amateur astronomers around the world observed it. Professional observatories studied it in detail. We learned a lot about the early evolution of Type 1a, explosions, how the light curve rises in the first few days, how the spectrum changes as the ejecta expand. PTF11 Cli was another nearby. Type 1, a supernova, about 21 million light-years away in the pinwheel galaxy M101. It was discovered very early, within a day of the explosion, that let astronomers observe the shock breakout. The moment when the shock wave from the explosion reaches the star's surface. For the first few hours, the supernova was hotter and brighter than expected. This was the shock breaking through the outer layers. It's the first time shock breakout was clearly observed for a Type 1, a supernova. That observation confirmed details of the explosion mechanism. SN 2011. DH was unusual in a different way. It was a Type 2b supernova, showing both hydrogen and helium in its spectrum initially. But more interesting was its progenitor. Before the explosion, the Hubble Space Telescope had imaged that region of the galaxy. After the supernova, astronomers went back and looked at those images. They identified which star had exploded. It was a yellow supergiant, not a red or blue supergiant. This was unexpected. It told us that massive stars can explode in different evolutionary states, not just as red supergiants. The progenitor had lost most of its hydrogen envelope, but not all of it. That's why the supernova showed hydrogen initially, but then faded. These are just a few examples. Every supernova is a unique event. The progenitor star had a specific mass, composition, rotation, and evolutionary history. The explosion had specific asymmetries and dynamics. The surrounding environment was unique. By studying many supernovae, we build up a statistical understanding. We learn what's common and what's rare. We test our models against observations. We refine our theories. Slowly, the picture becomes clearer. As we look to the future, supernova research will benefit from new observatories and detectors. The upcoming Vera Rubin Observatory, formerly known as LSST, will revolutionize transient astronomy. It will scan the entire visible sky every few nights. It's expected to discover tens of thousands of supernovae per year. That's more than all the supernovae discovered in the entire history of astronomy. This flood of data will let us study rare types of supernovae. Currently, we've observed maybe a few dozen superluminous supernovae. Rubin Observatory will discover hundreds or thousands. We'll be able to study them statistically, understand their diversity, constrain their progenitors and explosion mechanisms. We'll also discover transients we haven't even predicted. Whenever you increase sensitivity and observing cadence by orders of magnitude, you discover new types of events. There are probably classes of stellar explosions we don't know about yet. We'll find them. Next-generation gravitational wave detectors will also transform our understanding. LIGO and Virgo have detected neutron star mergers. Future detectors like Einstein, Telescope, and Cosmic Explorer will be much more sensitive. They'll detect neutron star mergers out to much greater distances. They'll measure the properties of neutron stars more precisely. The equation of state of nuclear matter, the maximum mass of neutron stars, the rate of neutron star mergers. All of this connects directly to supernova physics, because neutron stars are the remnants of supernovae. Understanding neutron stars better helps us understand the core collapse process that created them. Neutrino detectors are being upgraded and expanded. Current detectors like Super Kamiokande in Japan and IceCube at the South Pole can detect neutrinos from a galactic supernova. Future detectors like Hyper Kamiokande and Dune will be much larger. They'll detect thousands or tens of thousands of neutrinos from a nearby supernova. That will give us a detailed picture of the core collapse. We'll measure the neutrino emission over time. See how it evolves during the collapse. Detect different flavors of neutrinos. Measure neutrino oscillations. Test models of core collapse with unprecedented precision. The challenge is that galactic supernovae are rare, 1 or 2 per century. So we're building detectors that might operate for decades, waiting for the next one. But when it happens, it will be worth the wait. Multi-messenger astronomy, combining electromagnetic observations, gravitational waves, and neutrinos, will give us a complete picture. For a galactic supernova, we detect the neutrino burst first, hours before the optical light. That would alert us to start observing. By the time the light arrives, every telescope would be pointed at it. We'd get spectra, light curves, polarization, everything. We'd detect gravitational waves from the core collapse itself. Those waves encode information about the dynamics of the collapse, the formation of the neutron star or black hole, asymmetries in the explosion. Combining all three messengers, electromagnetic, gravitational, and neutrino, we'd learn more from that one event than from decades of theoretical work. It would be a golden opportunity. The search continues for the next Milky Way supernova. We know it's coming. We just don't know when or where. It could be tomorrow. It could be in 100 years or 1,000. But astronomers are ready. When it happens, the scientific community will mobilize. Every available telescope will observe. Data will pour in from across the electromagnetic spectrum. Neutrino detectors will catch the burst. Gravitational wave detectors will search for signals. It will be the most thoroughly studied astronomical event in human history. And it will advance our understanding of supernovae immeasurably. As we come to the end of this exploration, let's reflect on what supernovae mean for us. On a practical level, they're cosmic laboratories. They produce conditions we can't replicate on Earth. Densities higher than atomic nuclei. Temperatures of billions of degrees. Magnetic fields of unimaginable strength. By studying supernovae, we learn about physics in these extreme regimes. On a cosmic level, they're engines of creation. They forge heavy elements and scatter them through space. They trigger the formation of new stars and planets. They regulate galaxy evolution. On a philosophical level, they connect us to the cosmos. The atoms in our bodies were made in stars. Many of those atoms were scattered into space by supernovae. We are, quite literally, made from the ashes of dead stars. That's not a metaphor. It's a fact. When you look at your hand, you're seeing carbon and oxygen and iron that was once in the core of a massive star. That star burned for millions of years. Then it collapsed and exploded. The debris spread through space, mixed with the interstellar medium, eventually became part of the molecular cloud that formed our sun, and our planet, and you. That connection is profound. It means we're not separate from the universe. We're part of it, products of cosmic evolution, children of the stars. And that's what actually happens during a supernova. A star dies. The universe becomes richer, and the cycle continues. Thanks for staying with me through this journey into one of the universe's most violent and creative events. The next time you hear about a supernova discovered in a distant galaxy, you'll know what really happened. Not just a star exploding, but a core collapsing in less than a second. A shockwave, stalling and being revived by neutrinos. Layers of fusion products being blown into space at 10% the speed of light. Heavy elements being forged and scattered. A neutron star, or black hole, being born. And the galaxy being enriched, one supernova at a time. building toward the complex, element-rich universe we live in today. Keep looking up,